All right. Most importantly, we have a test next Tuesday, right? So we're going to have test number 2 on Tuesday, November 17th. So test number 2 is on Tuesday, November 17th. And so we're not going to have time to do a review class, but I will post the practice test just like I did last time for the test. And so you'll have a practice test, and it's going to cover chapters 2, 3, and whatever of chapter 4, which we're about to start today, we can get through on Thursday. So it will cover chapters 2 and 3. So chapter 1, not really, because we're kind of out of chapter 1, but some of those concepts have been in play this whole time, right? So that's why we do chapter 1. So chapters 2 and 3, and up to the end of class on Thursday this week. Oops, on Thursday this week, which is on chapter 4. So depending on how far we get, I don't think that we're going to finish chapter 4, so that's why I'm not going to put all of chapter 4 on there, but I do want to have a good chunk of chapter 4 done by the test. Okay, so for some review, right, we were graphing rational functions. Graphing rational functions. And so we were given kind of some step-by-step things that we needed to do. So the first thing we had to do was to factor the numerator and the denominator. Remember, a rational function is a polynomial over a polynomial. And so the first step is to factor actually, let's establish the general R of x is P of x over Q of x, where P and Q, P of x and Q of x are polynomials. First thing you have to do is, and we're assuming for now that P and Q don't have any factors in common, so it's already been simplified. And so the first thing we need to do is factor the numerator and denominator. Once you've factored those, what we established last day was, okay, once we factor those, we're able to find vertical asymptotes from the denominator and also the y-intercepts from the, the x-intercepts from the numerator. So it was kind of a double whammy. So that's why we factor both of them so that we have it and nicely available. Step 2 is to find the intercepts. The x-intercept, potentially more than one. You can have just one, right? And we'll see an example today. So the x-intercepts are where y equals 0, which can only happen, right? So where r of x, in this case, r of x is y. So where y equals 0 is only going to happen where the numerator is 0. Where the numerator is 0. Right? And so what's nice is because we've already factored the numerator, we can find the zeros very easily. Right? The y-intercept is where x equals 0, right? So what you do is you plug in x equals 0 into each of these and figure out what y is, what r of x is. And so finding the y-intercept is the easiest. I would recommend plugging it into the original equation unless you're super, super, super confident in your factoring, right? I encourage you to check your factoring, but it's always safest to just put it into the original equation. Your third step is to find the vertical asymptotes. Could be more than one, which will abbreviate VA because we'll have to write it out quite a bit. The vertical asymptotes are where the denominator is 0, right? So again, because we've factored the denominator and the numerator, right, we can easily find the vertical asymptotes. So where the denominator is 0. Okay. The vertical asymptote has that additional step of you pick test points, because what we want to know is how does it behave as we approach the vertical asymptote from the left and from the right, okay? And so we use test points to determine how the function behaves, as we approach the vertical asymptote from the left and from the right. From the left and from the right. That's probably the hardest part, or kind of the most tedious part. Step 4 is to find, and maybe, I guess I haven't been spacing them, okay, is to find the horizontal asymptote. Horizontal asymptotes, there's only one, for us at least. In fact, just generally, if it's a polynomial over a polynomial. So the horizontal asymptote, if we let n, or sorry, let a subscript n, x to the power of n, over b subscript m, x to the power of m, be the leading terms in R of x. Okay, so this is the degree of the numerator is called n. Is it Nicholas? M is the degree, M is in Michael, degree of the denominator is m. Okay. Notice that the leading coefficient of the numerator and the leading coefficient of the denominator are a over b, essentially. So if n is less than m, the horizontal asymptote is at y equals 0. Okay, so that's always going to be true. If n is equal to m, then you have a horizontal asymptote at y equals a subscript n over b subscript m. Just the leading coefficients as a fraction. That's only if the two degrees are the same. And then finally, if n is greater than m, then there is no horizontal asymptote. Okay. So those are your three scenarios. Clean that up a little bit. And that's how we determine the horizontal asymptotes. After you have all these pieces, then we can make a sketch. Now, what I want you to remember is I'm not expecting you to be graphing whizzes or anything like that, but I do want you to incorporate all these pieces that you've learned, right? Where are the intercepts? Where are the asymptotes? How do they all factor together? Likely, but then check your work in Desmos. So your fifth step is to sketch by incorporating all the information from above. Information from above, okay, and then use Desmos to confirm. Sometimes I'll admit that you'll go to Desmos and feel pretty good about your sketch, and that's, oh, I forgot about something. That's okay, right? We need to have these general ideas before we can get really good at sketching. And honestly, unless you keep going deeper and deeper into calculus, then just having a general idea of how to sketch is enough. Okay. So there was a special example that I wanted to show you guys. I wanted to show you functions, no. Where did I put it? I think I put it here. So down here, the example I'm going to do is 59. Notice on Moodle I posted all the solutions to the chapter 3 notes as well as the chapter 4 notes, feeling on top of things. So you'll have those solutions that you can work through the questions in the notes. So 59 is the one that we're going to do because it illustrates a special kind of scenario. So we'll call this the end of the review. And just as an example, we're doing 59 from 3.6. I think it was 59. Yeah. 59 from 3.6. Okay, pull it up here. So we have r of x is x squared minus 2x plus 1 divided by x squared plus 2x plus 1. Now something like this, notice that you're only dealing with quadratics and things that are kind of easy to factor, and that's all I expect of you, right? This isn't a factoring question, it's just factoring is something that we have to do to get to the answer. And so for here, you can absolutely use the quadratic formula to factor this. I'm just going to look at this and say, okay, I need to find two numbers that have to add to -2 and multiply to 1. Sounds like -1 to me, right? And so this is going to be, oops, I guess I should outline my steps first. First, I'm going to factor. So r of x is going to be x minus 1 squared, right? X minus 1 times x minus 1. And I'll just confirm, right, that this is going to be equals x squared. Actually, you know what? I'm going to write it as, changing my mind as I go here, sorry. X minus 1 times x minus 1, oops, is equal to x times x is x squared, x times -1 minus x, and then -1 times -1 is plus 1. All right, looks like it checks out to me, right? X squared minus 2x plus 1, that's what I wanted, good. Doing the same thing, right, very similar. Looks like x plus 1 squared. So what I have is I have x plus 1 times x plus 1, I'm just going to expand it, and just to confirm, x squared plus x plus 1, right? X squared plus 2x plus 1. So just confirm. All right, so I've factored this thing. Notice that, just like I did earlier, right, x minus 1 times x minus 1 can be zipped up as x minus 1 squared. Okay. So I'm going to do that. X minus 1 squared divided by, and same thing in the denominator, x plus 1 squared. Okay. All right. The reason I wanted to highlight these is because I get these multiplicity m. So we call these multiplicities because the factors are actually multiplicity m. So focusing on the numerator, right? The factor x minus 1 is of multiplicity 2. Okay. So we're going to see how to deal with this, and this is kind of, it shows up in our sketch later, okay, which we need to keep in mind for our sketch, okay? And the reason is from section 3.2, we kind of glossed over it because we didn't need it back then. But from 3.2 here, I'll say from 3.2 notes, okay, what happens if, so if C is a 0 of P, okay, so, and we are using the same notation, so P is the numerator, and C, if it's a 0, it means that it's a value that makes the numerator 0. So here, I'll just say, if C is a value that makes the numerator 0, okay, and it's of multiplicity m, so in this case, right, we said we have multiplicity 2, then the shape of the graph of P near C is as follows. So if m is odd, then we actually cross through C, right? Depending on if we're going up or down like this. But the whole game is that we cross through C if we had an odd m. Whereas if m is even, which it is in our case, then what happens is if we're coming from above, then we kind of bounce off the x-intercept. And if we're coming from the bottom again, we just kind of bounce off the x-intercept again, okay? So we're gonna keep this in mind for when we're sketching, right? And we'll kind of make a note of it as we go. So now, for now, we've factored, and that's what's so special about this example that I wanted to show you, is when we have this multiplicity up here, then how the graph behaves at the intercept is going to be different depending on if m is odd or if m is even. Okie dokie. Step 2 is the intercepts. And remember, you have these notes in your section 3.6 notes. The steps that I'm going through are these ones, right? Sketching graphs of rational functions. We have to factor, we find the intercepts, we find the vertical asymptotes, the horizontal asymptotes, and then we sketch it. So the intercepts here, we'll start with the X-intercepts. Are where the numerator, which is x minus 1 squared, are where the numerator equals 0. So the numerator is x minus 1 squared. Okay. And I'm going to force this to equal 0 because that's the only way that y is going to be equal to 0. So what I can do is I can take the square root of this thing. If I take the square root of 0, it's just 0. So even though I have to take the positive and the negative version of 0, it doesn't matter. So we have x minus 1 is 0. And then x is equal to, if I add 1 to both sides, I get x is equal to 1 is the x-intercept. And then here, I'll just make a note. X equals 1 is an intercept of multiplicity 2. Okay. So we're just going to keep that in mind for when we're sketching, right? Because what it says, right, if we have a multiplicity of 2, we're just going to bounce off, right? Notice that we only found one intercept, but because we're just bouncing off of it, that's why we only have one intercept. So it doesn't run through it, it just kind of bounces off of it. For the y-intercept, it's a little bit easier. Y-intercept is where x is 0. Okay, so I like to use the original equation, so let's bring in that original copy. Unless you're really confident in your factoring, then go ahead and use your factoring one, but r of 0 is 0 squared minus 2 times 0 plus 1 divided by 0 squared plus 2 times 0 plus 1. 0 minus 0 plus 1 is 1. Divided by 0 plus 0 plus 1 is 1. So now we have the y-intercept is at y equals 1 and x equals 0. So y equals 1. What I'm going to do is I'm just going to make a note of these ordered pairs, right? And so here I have the x-intercept is at when x is 1, y is 0. And here the y-intercept when x is 0, y is 1. Kind of a little game going on there. It's not always the case, but it's fun when it happens. All right, so let's go. We found the x-intercept, we found the y-intercept, and so now we can keep going. We can find the vertical asymptote. So remember here in our steps, right? The vertical asymptote is where the denominator is 0. And then we have to figure out the behavior around that vertical asymptote or those vertical asymptotes potentially. So step 3 is vertical asymptotes. And that's where the denominator is 0. Is equal to 0. So in our case, right, it's easier to use our factored version. So x plus 1 squared is 0. X plus 1 squared is 0. So again, I can solve for x to figure out what value of x makes this 0. So I can take the square root, so I get x plus 1 is the square root of 0 is 0. So x plus 1, so x is negative 1. is a vertical asymptote. Okay. And what I'll do is, I'll see if I can squeeze this onto the same page here. Because what I'm gonna do, I've only got one vertical asymptote, so that's nice. It's kind of easy to deal with at -1. So now we need to figure out the behavior of this thing. And what I'm gonna do, just like before, when we had to figure out the behavior, the general behavior, we use the factored version, which is this, of the equation that we're dealing with. I'm just gonna put it here, kind of shrink it down a bit, okay? And just remember that that's the function that I'm dealing with here. And then what I do is I just pick, as x approaches -1 from the left, okay? So here I'm approaching -1 from the left, and the behavior as I approach from the right might be different. So I also need to do x approaching -1 from the right. So remember this notation where we had negative meaning from the left, positive from the right, right? Or from the positive direction from the negative direction. Okay. So I'm just gonna pick some values here, kind of close to -1 is what I want. I'll make them easy for myself, right? I'll do -2 here and 0 here, just to get a general feel for how this thing behaves. But what I'm gonna do is I'm gonna plug in the test values into here and see if I get a positive or negative value. Spoiler alert, if I'm squaring a number, it's always positive, right? Anything squared is always positive. Anything to the power of 2 is always positive. Anything to an even power is always positive. So I'm gonna get a positive over a positive on either side. So I get a positive over a positive, and you can check it. -2 minus 1 is -3 squared, it's positive. -2 plus 1, negative squared is positive. So positive over positive gives me a positive number. Same thing over here. If I use 0, 0 minus 1 is negative, but once I square it, I get a positive. Divided by 0 plus 1 is a positive. Positive squared is also positive. So I get a positive overall. I'm just trying to squeeze it in on the same page here. So what we know is that as we approach -1 from the left as well as from the right, is we get this positive increasing behavior. Okay. So they're both going to positive infinity. Okay. So that's a key part of our sketch here, because it's going to help us with our horizontal asymptotes, as we saw as well. How? Let's see. So I'm on a new page, so I'm going to kind of keep it at the top of the page. The fourth step is the horizontal asymptotes. So in this case, right, we have, oh, here is our original equation. In fact, I'm going to steal it here. Copy. Paste. Making sure that these are organized so that they're decreasing in powers. They should be. They're typically organized that way. But here I'm going to have n is 2 and m is 2. So we have the same degree for the numerator and the denominator. And if we flip back to our notes, right, in general, if n is equal to m, then we have a horizontal asymptote at the leading coefficient of the numerator over the leading coefficient of the denominator. So here, this is 1 over 1. An over bm is 1 over 1, which is just 1. So what I'm going to say is that since n equals m equals 2, we have a horizontal asymptote. I'll just use HA. At y equals an over bm, which is 1 over 1, which is 1. So at y equals 1, we have this horizontal asymptote. So things are going to approach. So as x goes to negative infinity and positive infinity, y is going to go to 1. All right. So we're ready to sketch this thing, sort of. Remember, I'm not expecting a masterpiece, but I am expecting all the components to kind of be on this graph. So what I'm going to do is I'm going to put a grid on here and kind of hope it works out, okay? Because they're really hard to move once I've put them on here. I'll put my y-axis here, I'll put my x-axis here. And let's just plot these things that we've learned as we went through. So the intercepts, I have an x-intercept at 1, 0, and keeping in mind that it's of multiplicity 2. Okay, so at 1, 0, and then the y-intercept is at 0, 1. So let's use 1, 0, and 0, 1. Okay, so those are my intercepts. I've got, my next thing was my vertical asymptote. I have one vertical asymptote at -1. I also know the behavior around here, so I'm going to keep that in mind. So let's say this is at -1. So here I have a vertical asymptote. And what I just established is that I have a horizontal asymptote here at y equals 1. Okay. So remember, the behavior around the vertical asymptote is that it's going to go to positive infinity on either side. So what I'm going to do is I'm just going to start and put those on, because that's all I know for certain so far, right? Is that this thing is going to go like this and like this. Oops. Okay. So I'm not committing to anything more quite yet. This side, well, if I know that this is a horizontal asymptote, then it's just reasonable that this thing on the left-hand side of the vertical asymptote is just going to trace down and then just kind of rest on the horizontal asymptote. It's never going to go to the horizontal asymptote, but it's going to approach the horizontal asymptote. Remember, we're just sketching. So that's my first thing that I'm going to draw on here, is just kind of have it go. As x goes to negative infinity, the y values approach the horizontal asymptote at y equals 1. Okay, now this side is a little bit different, right? Because I know that I have to cross at the y-intercept. So how about I draw that little section first? In fact, I've got a little crook here that I'm going to fix. Okay, so I'm going through the y-intercept. I know I have to do that. I'm allowed to cross the horizontal asymptote as long as the end behavior, so as x goes to infinity, then I have to approach the horizontal asymptote either from below or from above, whatever makes more sense. So another thing that I know is that, okay, well, I have to hit this x-intercept, right? So the graph goes through the x-intercept, but because it's of multiplicity 2, we know it just bounces off. And that's the weird part with this example. So what happens is it goes through the x-intercept or the y-intercept, and then it bounces off the x-intercept. And then as x goes to positive infinity, you approach the horizontal asymptote from the bottom, right? Because that's where you are. So kind of our best guess at this graph might look something like this, right? And here, oopsies, there. So this area here, since the X-intercept is of multiplicity 2, that's why it's bouncing off. So here's kind of my best guess at what this graph looks like. What I want to do is I want to check it in Desmos. A lot of this is trial and error. So like I said, I totally put it through the x-axis here, but then what happened was I didn't have a way out, right? So I knew I had to approach the horizontal asymptote, but if I cut it through the x-axis here, and there's only one x-intercept, there's no way for me to get back over the x-axis, right? So that's the problem. If we only have one x-intercept, then that's why we have to bounce off here. Okay. So let's graph it in Desmos to see what's going on here. Oh, that's for later. Hey, my screen sharing. It said it ended unexpectedly. We'll just try again, I guess. Okay. I don't know why I did that. Did that the other day. Maybe I need to restart my iPad or something. It's too tired. Oops. Okay. So what I'm going to do is I'm going to plot the original equation that we were given. Notice that it's a polynomial over a polynomial, so I'm going to put the numerator all in brackets to make sure it's all up top. So I have x squared minus 2x plus 1, and brackets, divided by x squared plus 2x plus 1. Okay, and because I was doing something weird here, I'm all zoomed out, but if I go and kind of zoom back in, right, I have that type of behavior that I was suspecting. Of course, I had already checked it to make sure that I gave you the right graph, right? But that's okay. That's kind of how these things are going to go. So just to make sure, I'm going to draw lines at my asymptotes to make sure that they're kind of where I thought they would be. So I have an asymptote at x equals -1, and that looks like it might be the asymptote, or it looks like it is the asymptote that we're following, so that's good. And I also had an asymptote at y equals 1. Okay, and so as we're approaching x negative infinity, as x goes to negative infinity, we're approaching y equals 1, and here we're approaching y equals 1 as x goes to positive infinity, but from below. Nice. Okay, so this is what it would look like, right? This red one. Notice our x and our y intercepts are on there as well. Okay, and so looks like we did a good job. All right, let me just make sure I'm not skipping anything here for you guys. All right. So the last thing in 3.6 that I want to talk about, because it might come up, is if we have some common factors in the numerator and the denominator, what happens? Remember that we've been assuming that we don't have any common factors. So here, nope, this one. I'm going to skip the slant asymptotes and end behavior. We don't really need to bother with that, so I'm going to skip that. So we've assumed, okay, that, and I'll make this bigger because we have the space. The numerator and the denominator of a rational function have no factors in common, right? Meaning they've been simplified as much as possible. If P and Q do have a factor in common, we're allowed to cancel that factor, but what we have to remember is that even if we've canceled that factor, it's still there in the original equation. So we need to keep that in mind for our domain, right? Our possible inputs. What happens is we can't divide by 0. So even if we've canceled a value, right? X equals 1, for example, or x minus 1, so x equals 1 would be taken out of the domain. If we've canceled that x minus 1, then we still have to pull out x equals 1 from the domain. So what happens is we get a hole at those points. So let's do an example. If we have s of x is x minus 3 divided by x squared minus 3x. Okay. What we have, right, we can factor out a common x here, and so we can rewrite this as x minus 3 times x minus 3. So now we have a common factor of x minus 3. What happened there? Common factor of x minus 3. Okay. Here, if I asked you what the domain is, well, you would know to check because I'm dividing. I can't divide by 0, so x equals 0 is out, and x equals 3 is also out of the domain. Since we can't divide by 0, x equals 0 is not in the domain. And x equals 3 is not in the domain. Even when we cancel x minus 3, which we're allowed to do, we're allowed to simplify this thing. But remembering that this is the original equation, x equals 3 can't go into the original equation. And so what happens is it's not in the domain, even if it's simplified. So what we get is we get x minus 3. I'll put it in brackets just to emphasize that they're the same, x minus 3. We can simplify this to 1 over x, right? As long as x is not equal to 3, right? Obviously, because we have 1 over x, x can't be 0 as well, right? But the added condition that x can't be 3, we can't see here. So even though we can't see that x is not equal to 3 in the simplified version, of the function, it is part of the original domain. Part of the original domain. Okay. So what happens is, well, at x equals 0, we can't have x equals 0. And what happens is at x equals 3, we have a hole. Okay. So in our graph, we will have a hole. Have a hole at x equals 3. Okay. So what I want to do is I want to show you in Desmos because it's actually kind of hard to see in Desmos. And then we'll draw just a quick version of the same thing. So here, hey, it seems like when I go to Desmos, it doesn't like it anymore. My screen sharing, I'll have to reboot after this class, I think. It doesn't like it anymore. Okay, back in business. So let's see here. See if I can go into Desmos, if it'll let me. My original equation that I had was in brackets x minus 3 and bracket, oh, xx. X minus 3 and bracket divided by x squared. Hey, why is it not picking up? X squared minus 3x and bracket. So notice that there's no hole here, but if you take your finger or whatever and you go to x equals 3, I'm having a hard time staying there. 3 is undefined, right? And so it's there, it's just the whole graph looks like 1 over x, right? So we get this kind of, this bow shape is 1 over x. It's one of those graphs that we kind of have a good handle on because it's one of our core functions. But what we get is we get this graph of 1 over x with a hole at x equals 3, and I'm gonna just erase this here like that. So it ends up looking like our simplified function 1 over x, but it's got this hole at x equals 3. Yeah, right there. Okay, great. So that's the end of chapter 3. 3.6 is a big section, right? Because we're graphing, we're finding these asymptotes, all that fun stuff. But just follow the steps, right? Factor, find your intercepts, find your vertical asymptotes, find the behavior, find your horizontal asymptotes using those guidelines, and then do your sketch. Right? And then here, I just wanted to show you what happens with the holes in case it comes up, but it's not something I'm going to focus on. Okay. Any questions before we get into chapter 4? No? Okay. So I've posted the notes for chapter 4. Like I said, we're going to see how far we get by the end of next day, and then whatever we get through this week will be on the test next week. So, but of course, I know you're just seeing it now, so I'm going to keep it nice and light for the test, and then we can test it again at the end of the term. So chapter 4, there are no questions, is on exponential and logarithmic functions. I have to really focus when I write logarithmic, because I always want to just squish it up, but logarithmic. Okay, so exponential and logarithmic functions will be on the test, and I'll just emphasize that here. Chapter 4 will be on test 2. everything covered this week. Everything covered this week. So we'll kind of see how far we get in chapter 4. I don't think we're going to be able to finish it, but pretty close. All right, so 4.1, let's start talking about what is an exponential function. So an exponential function let's go to the notes. Oh. So 4.1, we start and we talk about exponential functions. What's special about an exponential function and what makes it an exponential function is the x is in the power, right? We need some terminology, just like we had to know what the numerator and the denominator are for fractions to be able to talk about them. We need to know that a is the base. So whatever the base is, I don't know how else to say it, we call the base. So a is the base, and what I'll say, I guess it's more of a regular note, an exponential function is when the x is in the power. An exponential function is when the x is in the power. Okay, so if we have something like f of x equals a to the x, right, now we've got x in the power. We're gonna use some conditions on a, the base. The base has to be greater than 0, so we're not gonna use a base of 0. 0 to the power of anything is just 0 times 0 times 0 times 0, and that's not very interesting. So we're gonna not use a is equal to 0, and by the same logic, we're not gonna use a equals 1, because if you have 1 to the power of 3, for example, that's just 1 times 1 times 1, and we know what that is, it's just 1. So that's boring. And so here we're just going to establish that the base is not going to be greater than 0, or is not going to be less than or equal to 0, and it's not going to be 1. Okay. And so recall, we've already actually used it. Oh, I need to change my eraser. Recall that if you have 3 to the power of 4, right? Or actually, I'm going to use a to the power of 4. That's a times a times a times a, right? 4 times. So exponential functions are just letting you vary how many multiples you have, okay? And you've probably heard of things like exponential growth. Oh yeah, things are growing exponentially. And what that's saying is that it takes off. So it kind of starts slow and then things just kind of grow exponentially. So they grow really quickly. Okay. And so that's what we're going to talk about when we're talking about exponential functions. So the next little blurb I want to talk about is this one. Okay, so here, move this there. Depending on what the base is, okay, and maybe I'll move this over a little bit so I can write on this side. Depending on what the base is, if you have an a greater than 1, right? So still a is greater than 0 and a can't be 1. But if a is greater than 1, then you have this upward action, right? We call this exponential growth. exponential growth if a is greater than 1. Here, notice that we have the same behavior, but we're on a downward slope. So here, a is between 0 and 1. So it's still greater than 0 and not equal to 1, but it's some value like 0.75, for example. So it's some fraction between 0 and 1. If our base is a fraction between 0 and 1, then we have this exponential decay, right? And so a lot of kind of minerals decay, right? And medicines decay, right? There are a lot of things that decay. So here we have exponential decay if a is between 0 and 1. Okay. What's nice about exponential functions is that the domain is always from negative infinity to positive infinity, so the set of real numbers. So the domain is, you can either write x is in the set of real numbers or from negative infinity to positive infinity. So we can plug in any value of x is allowed in here, and we can find the exponential equation. The range is going from 0 to infinity. Now the reason for that is, and you can see it graphically, right? It goes towards the x-axis, but it doesn't ever approach it. So we've got this asymptote at y equals 0. But so the line y equals 0 is a horizontal asymptote of f. Okay, so it's never approaching y equals 0, but it's going to go to 0, and then it's going to increase to positive infinity depending on, you know, which direction you're going. So the reason we can't have negative values, or one of the kind of crutches that we have, is that, well, I don't have a negative base, right? So right off the bat, I've established that a is greater than 0. So I'm not able to have a negative 3 to the power of 15, for example, right? Which would give me a negative number because it's an odd power. So I've already established that since my base is positive, then my y has to be positive always. So the range for this thing, regardless of if we have growth or decay, is always going to be from 0 to infinity. Okay. So that's good to keep in mind. Let's just do a quick example, and I am stealing it from here, so I guess I'll show it. I don't want to do a ton of these. I just want to make sure that whatever you're using as your calculator, it's behaving the right way. So let's do 10. Do these to make sure you know how to use your calculator. I know that sounds stupid, but you just want to make sure that you're using your calculator correctly. You know how to use your calculator. So we're just going to do a few here. So if g of x is 4 over 3 times 3x. Okay, so x is in the power, which means I have this exponential function. My base is 4 over 3, which at first glance looks like a fraction, but 4 over 3 is actually greater than 1. So I can already tell that I'm going to have this growth function. And then to the power of 3x. Now g of -1/2. Okay, here we go. G of -1/2 is 4/3 times 3 times, or to the power of 3 times -1/2. I'm going to use the Desmos calculator so you can see it on the screen. It's not, my iPad doesn't like sharing my Desmos anymore. Share screen. Come on. Okay, it looks like back in business. I'll try to not confuse it so much, and maybe I'll just do the calculations on the side, but just for these where we need to make sure that we're doing it correctly. So we've got 4 divided by 3, and notice that I'm going to put brackets around this thing, right? 4 divided by 3, and then all to the power of, and also in brackets just to make sure that everything stays in the power, 3 times -1 divided by 2. And then I'm going to step out those brackets. Hey, there. So you should have 0.6495190528. Unless I did something wrong. 4 to the 3. You know what? I'm going to put this -3/2 just to make sure. Okay, good. So 0.6495. This is, oh man, okay, this is not fun. I guess I can't go to Desmos anymore. It doesn't like it. Hopefully it'll hang in there. Okay. Okay. Keeps bumping me out. Okay, sharing my screen, going nice and slow. Okay. Well, that's not what I wanted to do at all. Okay. Come on. I'll try one more time, and then if it doesn't work, we'll take a quick break, I guess, and I'll restart my iPad. Okay. Okay, so hopefully we can just stay in here. I hope I don't forget and try to go to Desmos again. So if we do, now I have to, because I've completely forgotten, 4/3 to the power of, and then -3 divided by 2 is what I can simplify that to. And whenever I'm doing a decimal approximation, I want to use the approximately equals. So 0.6495190528. Okay. And let's do the root 6 one. So g of root 6 is 4/3 times 3√6. So roughly equal to 4/3 to the power of, and then in brackets 3 times the square root of 6 in bracket. I get roughly 8.281489611, roughly. Okay, so just make sure that that's what you're getting when you when you do your calculations. Okay. All right. Hopefully it lets me switch between pages in Notability at least. So these functions, okay, let's just get a general idea of what these things look like, right? So here we have a series of exponential functions, all with x in their powers, right? And so here we start with the yellow one, and that's our first decay model, right? And so look at 1 over 10 is our base, 1 over 5 is our base, 1 over 3 and 1/2 is our base. And these are all going to be decaying models, right? So we've got this exponential decay, and it looks like the smaller our fraction is, so 1 over 10 is the smallest one, 1 over 2 is the largest one. It looks like the smallest one is closest to the y-axis, right? And then it just kind of, so this is like the sharpest exponential decay. And then for 1/2 to the power of x, we kind of have this more shallow decay. Same sort of idea for when we have whole value bases, so whole numbers greater than 1. And so if we have 10 to the power of x for any value greater than 1, 10 to the power of x is our highest base here, 10, 5, 3, 2. And it's going to be closest to the y-axis, which means it's going to be kind of the steepest of these growth models. And as the base becomes smaller or closer to 1, right, it starts becoming more and more shallow. Okay, so these are the general behaviors of these things. I want to do one of these because it might come in handy for, and you know what, I'm going to just crop, whoops. Hey. Crop. So I can have it on this page here. We're going to do 21. Okay, so find the exponential function f of x equals a to the x whose graph is given. And I think, I can't remember if you had one or two like this on your assignment back in the quadratics for 3.1, but you might, where you're given a point. A point is information about x and y, right? I think there might, in 3.1, the assignment for 3.1, there might be a question where you're given the vertex and a point on it, and then you have to construct the equation. But just remember, when x is 2, y is 9, right? And so here, for 21, we have x, y is 2, 9. So what we have is f of x, which we can replace with y. We can just read it as y equals a to the x. Well, when y is 9, x is 2. 9 is a to the power of 2, which if we take the square root here, right, taking the square root is a little bit finicky because we have the plus minus root of 9. What on earth? Which is equal to a. Okay, this is plus or minus 3. Okay, but since a has to be greater than 0, it's just going to be positive 3. Since a is greater than 0, we know a is equal to 3. Okay. So f of x is 3 to the power of x. Which you can confirm using Desmos, but I'm not going to do that because it keeps kicking me out. Okay, So that's a good trick, right? If you have 1 point, then you actually have an X and a Y coordinate, which you can use to solve for unknown values. Okay. What's fun about exponential models is we have a kind of real world application. So compound interest is used by the banks. And so the banks would be using this formula. And we just need to talk about, well, what each of these things are, and then you'll be able to use it. Compound interest, so the idea behind compound interest is, let's say you have $100 and you go to the bank because they offer you interest, right? And so we all know that we want to earn interest on our money. Right now it's not a lot, right? But there have been times where it was significant. And so if you have $100, you go in and they tell you, great, we're going to give you 4% every month. Okay? So what happens is, on that $100 that you deposit, you earn your interest, the 4% compounded monthly. So the 4% is over the year, but every month you get a portion of that 4% added on to your $100. So by the 11th month, you're earning interest on interest that you've already made, right? And so that's where the compound comes from. And if you're interested, this is the type of math that we do in business math, so Math 114. It's really fun, and if you're just looking for like a fun math course to do, business math is a good one. Okay. You might have to be in the business program, I don't know. I think they probably have a few where you're not in the business program. Okay, so what we have is we have this formula, and what's nice about, for our purposes, I'm always going to give you the formulas that you need, right? So you're not going to have to develop them, because that can be really difficult. So what we have is the compound interest. So A of t is the amount of money after t years. So t is in years. P we call, uh-oh. I lost my screen again and I didn't do anything. Come on. Okay. Can I go slow still? Nice and easy. I don't know why it doesn't want me to share my screen anymore. So P, P is the principal amount, which is also kind of our initial investment. So the initial investment. And as long as we have everything, all the information except for one piece, by the end of this chapter, we'll be able to solve even for n and t, right? Which is kind of hard because we don't yet know how to solve for something in the power. So for now, we're just going to solve for a of t, p, r, and n. Well, not n because n is up here. But a of t, p, and r we can solve for because it's just math. So P is the initial investment, and R is the rate as a decimal. That's important, right? Because something like 3% is going to be 0.03, really affecting our math, right? If you use 3 versus 0.03, you have to divide it by 100, right? Even though we usually talk about rates as percentages, we have to use decimals in our math. N is the number of times interest is compounded per year, and then T is the number of years. Okay. I'll underline the years because sometimes that can be tricky. So let's do an example here. Hopefully it doesn't kick me out again. Let's just do this first one. And then I think you'll have the idea for the rest of those. And like I said, I already posted the solutions to all these on Moodle. So you can work through these and just kind of check your work. So we're going to do just A here. And then we'll move into 4.2, which is a lot more of the same. It's just a special base. So 57A. Okay. Hey, 3%, that's nice. That was a coincidence. So what I'm going to do is I'm going to copy down the formula, and then I'm going to fill it in with the information that I'm given. So it says if $10,000 is invested at an interest rate of 3% per year, compounded semi-annually, so semi-annually means 2 times per year, find the value of the investment after the given number of years. Now, I'm not expecting you to know what semi-annually means. Of course, if you're just working on an assignment, you can just Google it, right? But for a test, no, I don't expect you to know. Semi-annually is twice per year. Oops. Twice per year. Okay. So what I've got, if I'm filling in this equation, right, find the value of the investment after the given number of years. So what I'm finding is the amount after t years, where t is 5 initially, and we'll just do 5, and then you'll be able to see 10 and 50. So we have a of t, just copying down the formula, is p times 1 plus r over n to the power of n times t. In our case, I'm going to fill in the information that we have, right? P is 10,000 because that's my initial investment. So I have 10,000 times 1 plus R is 3%, which I have to convert to 0.03. Divided by N, which is 2, right? 2 times per year, which I'll make a note of here, N equals 2. All to the power of 2 times t, so that's for a of t. Now, for part A, I want to find where t equals 5, right? So all I'm going to do is I'm going to replace that t with 5, and so I get a of 5 is 10,000 times 1 plus 0.03 divided by 2 to the power of 2 times 5. Okay, so now I get 10,000, oops, clean that up. And what I need to do is, bed mass is still a thing, right? So inside my brackets, I have to deal with my multiplication first before I can move on to the adding. So I want to start inside my deepest brackets and kind of bloom my way out. So 0.03 divided by 2. Here, I get 1 plus 0.03 divided by 2. Use your calculator. 0.03 divided by 2 is 0.015 to the power of, and I'm just going to simplify, 2 times 5 is 10. But now I'm going to do 1 plus 0.015 before I go ahead and do this 10. This is probably the most common place where math errors happen, right? Is you want to take 10 and maybe bring it in or do something weird, but you have to deal with your brackets first. So plus 1, 10,000 times 1.015, and then to the power of 10. Now my next step is going to take 1.015 to the power of 10. So I'm at 10,000 times 1.160540825. That's an approximation, but I think it's close enough. Right. You never want to round too quickly, because this is money that we're talking about, right? So I mean, depending on the amount here, if we're talking millions of dollars and you've rounded and rounded incorrectly possibly, then you're losing a lot of money, right? It's kind of it depends on how much money you've got invested, right? But every dollar counts. So now if we multiply that 1.16 times 10,000, I get 11,605.40825. Okay. And what we're going to remember is that money only has 2 decimal places. Money has 2 decimal places. Okay. And up here, you have to keep as many decimals as you can, as possible. In fact, it's best if you just keep that whole number in your calculator and use it to multiply by 10. So what we get is we would end up with a total of $11,605.41. Okay, good. So like I said, work through those problems because they're kind of fun money problems and definitely worth it for the real life aspect. We all have money to some degree. So we need to know how to do those calculations, or at least understand what's going on there. Okay. I want to get into 4.2 because it's just an extension of what we just did, exponential functions, but it's the natural exponential function. And the natural exponential function. Okay. So the natural exponential function has a special base, and it's just the base e. Okay. So e to the power of x might be familiar, right? And so we call it the natural exponential function is just e to the power of x. E is a constant, just like pi is a constant, and it never ends. So e is often on your calculator, and if you want to know what e is, you do e to the power of 1. Now, because my iPad keeps kicking me out whenever I change screens, I'm not going to be able to show you in the Desmos calculator. But if you do e, oops, on your calculator, e to the power of 1, you should get, so e is a constant like pi, but we can approximate e. E is approximately 2.7182812828. There's a song, I can't remember how many decimal places it predicts or it approximates e to, but 2.7182812828, and then it just keeps going and going and going. And notice that this is a decimal approximation. So for exact answers, you would have to use the letter e, right? Just like for exact answers, we would use pi. We haven't done a lot of trig yet, so we haven't really seen pi, but I think we all know pi. E to the power of x is so common in so many places that it's actually often called the exponential function, right? but any exponential function is where x is in the power. So really what we're doing is we're doing roughly 2.718 times 2.718 times 2.718 x times. So what happens is the graph of e to the x, and there is information on kind of what e is. So if you go back to the notes here, there's some information on what e is. I'm going to leave that for if you go into calculus. We talk about it in calculus and we kind of use this in calculus. For us, as long as we understand that it's a constant and kind of understand what the graph of it looks like, that's good enough for us here. So what happens is y equals e to the x. Well, e is somewhere between 2 and 3, right? And so 2 to the, and it's going to be closer to 3 to the x than 2 to the x, right? And so notice that all of these go through 0, 1. And so it has this exponential growth with a base of 2.71828. Okay. So there's an example in here on an exponential model for the spread of a virus, and I'm going to zoom in here. Notice that E is in here, but because these solutions are in the notes, I'm going to leave those for you to walk through. And then what I want to do is I want to maybe talk about 23. And we'll go through 23 instead. So this is the type of scenario that you might have. Drugs decay, right? And so when a certain medical drug is administered to a patient, the number of milligrams remaining in the patient's bloodstream after T hours is modeled by 50 times e to the negative 0.2 t. How many milligrams of the drug remain in the patient's bloodstream after 3 hours? So t is 3. All we have to do is plug in d of 3 and figure out what it is. At t equals 3, d of t is 50 e to the negative 0.2 t. So d of 3 is 50 times e to the negative 0.2 times 3. Now, when I have to do these, I like to simplify the power first. You don't have to, as long as you know how to find e to the power of something on your calculator, right? So that's why you have to practice a little bit. E to the power of, to the power of negative 0.2 times 3. Okay, just to check in, this is 50 times 0.5488116,361, and then times 50, just so you have kind of the idea here, right? I'm showing that e to the negative 0.2 times 3, you should have 0.5488, 27.4405,818. Okay. You could spend some time talking about milligrams and just, okay, do they want a whole number? Should I be rounding this? As long as you've got this full, all the decimals here, I'm happy, right? So I would mark this as correct. I'm not going to be too nitpicky about, oh, it should be a whole number here, unless it's obvious. And you'll know what I mean, because I'll show you when it's important, right? You can't have half a person, for example. So when we talk about populations, so here we can have 0.44 of a milligram, or a milligram, right? So that's allowed. You can't have 0.44 of a person. So that's when we would need to round either up or down, depending on the scenario. Okay. So I want to talk about logistic growth. So that's example 27. And then that should be good for today. So like I said, populations are often modeled using exponential models. Notice that t is the variable and t is in the power, so we have this exponential model. So animal populations are not capable of unrestricted growth because of limited habitat and food supplies. So this happens in nature, right? Where you introduce fish into a pond, I think is what we'll see. The pond is only so big, so the population will only be able to handle a population of a certain size. And so if that's the case, then we have a logistic growth model, which looks like this in general, where C, D, and K are positive constants. And so C, D, and K are just constants, which will be given to you. For a certain fish population in a small pond, D is 1200, so 1200, K is 11, and C is 0.2, and T is measured in years. Okay, that's important. If it says, 14 months, you have to convert it to years. The fish were introduced into the pond at time t equals 0. How many fish were originally put into the pond? So what we can do, right, the population is the population size, so P of t is the population size, and they were introduced at time t equals 0. So what we're finding is P of 0. Here, find the population after 10, 20, and 30 years. What we're finding is P of 10, P of 20, we're just going to do P of 10, and then P of 30. Evaluate P of t for large values of t. So what we're going to do is we're going to use the graph. What value does the population approach as t goes to positive infinity? So as time goes on, does the graph shown confirm your calculations? So I'll bring in that graph that I cut off. I'll put it over here. Okay. So the behavior is going to be something like this, right? Where we have this kind of exponential growth, but then what makes it logistic is that it has this kind of cap on it and it starts to plateau. And so it starts off as exponential growth and then it kind of like snakes off. So for A, P of 0, well, actually, let's establish what P of t is. P of t is D, which is 1200, divided by 1 plus K, which we're told is 11, and then E to the negative C is 0.2 t. Okay. So P of 0 is 1200 over 1 plus 11, and E to the power of 0, right? 0 times negative 0.2 is just 0. One thing to keep in mind here, and this is going to be really useful, really kind of make your work a lot quicker, is that E to the power of 0 is 1. Okay, so what happens is 11 times E to the power of 0 is just 11, so 1 plus 11 is 12, so we get 1200 divided by 12, which should be 100. So initially 100 fish were in the pond. How many fish were originally put in the pond? 100. Therefore, 100 fish were originally put in the pond. We want to find P of 10. Let's start there. P of 10, well, same idea here. I'm going to use this equation, so 1200, and then instead of t equals 0, I'm going to have 10 now, so it's going to be a number, or an interesting number, I should say. 1200 divided by 1 plus 11 e to the negative 0.2 times 10. So here's where you want to make sure that you know how to do these calculations. So I'm going to start down here, e to the negative 0.2 times 10. So negative 0.2 times 10 is negative 2. Okay. And e to the negative 2. So I'm going to write out each step as I go through. You don't have to show this much work, but it's just in case you're referring back to it. Then it's got the step-by-step how I approached it. So from here, I went to negative 2. So e to the negative 2 is roughly 0.1353. And keep as many decimals as you can. Oops. 0.135335282 times 11 and plus 1. I'm going to cheat because I'm running out of space there. And then 1200 divided by, okay, fine. 1200 divided by 2.488688116. Keep as many decimals as you can and write them down. It's not that bad. 688116. Now 1200 divided by that. Usually you'll have a recall button on your calculator. If you've got something like this, I've got an answer which just inserts the previous answer. For these types of calculations, it makes it a lot easier. So get to know your calculator. But what we get is approximately 482.1817537. For a population, right, we would probably say this is 483 fish, right? Or closer to somewhere between 482 and 483 fish after 10 years, right? So just a prediction anyways. So what I'm gonna do is, therefore, there are approximately 482 fish after 10 years. And lucky for us, I screenshotted in Desmos. Let's see if I can grab it here. What I wanted to show you. So, haha, joke's on Zoom or my iPad. I don't know which one's booting me out. Okay, so, I don't know what happened. I lost you guys, but it seems like we're still going. So just hang in there. I got to restart everything, I guess. So one thing that's important here is when you're doing E, it's actually EXP in the graphing. So this is important, okay? And you have to use brackets. So EXP and then brackets is pretty typical for e to the power of something in some sort of programming language. So the blue graph is our logistic growth, okay? So here is x equals 20, population size is 998.77, at t equals 30, x and t are interchangeable since they're the inputs. So when after 30 years we have 1,168 fish-ish, and as time goes on, the pond seems to only be able to handle 1,200 fish in total, right? And so we get this kind of plateau action. All right. So I'm going to leave it there because I'm having too many computer issues. But are there any questions? So we'll keep going in 4.3 next day and have a read through those notes that I posted so that you kind of know what's coming up ahead in chapter 4. All right, I'll stop this.